All right, this is the distributed analytics using Apache Spark and Couchbase. So just make sure you're in the right space. If you're looking for Apache Spark, Couchbase, you come to the right place. All right, my name is Jason Pohl. I'm from Databricks. I'm a solutions architect there. I work with customers to make sure that they become successful with Apache Spark on the Databricks platform. And I'm joined by Michael Nitschinger.
Yeah, pretty good. Yeah.
Pretty good. From Couchbase, who is, he's developed a Spark connector. So I'm just going to begin. For a quick show of hands, how many of you have heard of Apache Spark? That's a pretty good, fair number. All right. How many of you have heard of Databricks, the company? It's a fair number as well. All right. So as you probably know then, Apache Spark was created in the Berkeley Lab. I'm sorry, the Berkeley Amp Lab. Yeah, sorry. And the creators of Apache Spark are the co-founders of Databricks. And so what we do at Databricks is we offer a just-in-time data platform where we host Apache Spark as a service for you. And you can essentially spin up Spark clusters on demand easily in the cloud and then attach either jobs or notebooks to them so you can begin doing either data science and making machine learning models or doing data engineering, where you're running some ETL flows across your data, or just doing data analysis and exploring your data. And we make it pretty easy from a notebook point of view, as well as schedules jobs. So Apache Spark, open source data processing engine, and then Databricks is the company that hosts these open source clusters in the cloud for you. And if you may or not know this, but Apache Spark is the largest, most popular open source big data project out there right now. So really quick, so with Apache Spark, you've got the core API. This is where originally, using RDDs, resilient distributed data sets, you can take any collection of data and distribute it across a cluster of computers and then work with it in a resilient way so that if you lose some of your nodes in your cluster, your jobs carry on. That API, it's built in Scala, runs on the JVM, but you can write projects for it, or programs, applications, using Java, Scala, Python, SQL, and R. And so the idea is that you should be able to use whatever language you're most productive in to be able to interact with your data. And on top of the Spark core API, there's a few other libraries that have been developed over the years. So Spark SQL and data frames, they're one and the same, but essentially they allow you to write SQL against your data, wherever that data might reside. Streaming, prior to Spark 2.0, which was released earlier this year, there was Spark Streaming, and now with 2.0 we have Spark Streaming and additionally structured streaming. And these are two different streaming engines that allow you to essentially take data from a source, join it together, do some transformations, and then sync it out someplace else and keep that running on a continuous basis. MLlib is our machine learning library, so you can use this to build machine learning models, predictive models, anything from predictive engines or recommendation engines. And then finally, GraphX. GraphX was the first iteration of being able to do computation on graphs. We've since released another package called Graph Frames. And so this allows you to essentially do the same things as GraphX, but utilize the data frames implementation. And data frames go through two levels of optimization. Project Tungsten, which does off-heap memory management, as well as the Catalyst Optimizer, which allows us to plug in different optimizations from data over time. So a little bit of analogy here for you. Did anybody ever have one of these first cellular phones where it's like it's in a big bag, you had to carry it around? Anybody? Any hands? All right, there's a few in the back there. All right. So this was like the first cellular phones. It was it doesn't look cool today, but it was pretty cool back then. And then what would happen is you had a proliferation of devices, and people would actually come up with like vests, so you could have all these different pockets to hold all your devices in. And you might have had a Nokia phone, as well as a Palm Pilot, and a different device for your GPS, right? And so there's very specialized devices that you could take on the road with you. And now what's happened is we've kind of brought all those devices together into one device, a unified device. And with this one unified device, you can do things that you could never do before with any of those devices. For example, there's an app called Waze. I don't know if you ever use it. But Waze is something where basically it monitors all the people who have the Waze app how fast they're moving down the road. And then Waze can actually not just give you GPS directions on where to go, but it can tell you how fast traffic is moving in certain places. And so we see the same thing happening, history repeating itself, with big data in general. So in the beginning, with big data, the first platform to really get popularity was the Hadoop platform, which came out roughly 10 years ago. And then Hadoop was a way to basically take your data, however big it might be, distribute it across a cluster of computers, and then do processing on it. And then what happened is all these other projects came about to help do specialized use cases. So if you wanted to do general processing, you had MapReduce. If you wanted to use SQL on your data, you had Hive. If you wanted to do like some PLSQL type stuff, you could use Pig. If you wanted to do streaming, there was Storm. And then the list goes on. And so now what we're seeing is a unifying of data architecture for one unified data processing engine, which is Spark. And Spark allows you to do the machine learning, the streaming, the SQL, all in one engine. So you don't have to learn 5, 6, 12 different projects. You just have to learn one common API that you can extend with libraries and connectors. And today we're going to talk about the Couchbase connector. Just to drive home the point, this is a Google Trends search on the terms people have been searching for between Hadoop and Spark. And you can see roughly around October 2014, the search terms for Spark exceeded that of Hadoop. And it's been growing ever since. So we just came out with Spark 2.0 this year. We're on version 2.1 right now, or 2.01 right now. And some of the features that came out of 2.0, we have performance improvements. So I mentioned Project Tungsten before. This is what the data frame interface uses. And what we had is we've optimized some of the queries that are running there. And we found that we have speedups of over 5 to 20%, or 5 to 20 times faster than was running before. So I've worked with customers that have gotten 10 times faster performance from the same queries that they were running on Spark 1.6 libraries. And this is because Tungsten allows us to basically manage memory off heap and take more of the things that are being managed within the JVM outside and do things faster with using less memory. Structured streaming engine. Prior to 2.0, the only way to do streaming in Spark was Spark streaming. What we've done is we've talked to a lot of customers that were building Spark streaming apps, and we realized that a lot of them were doing more or less the same thing. So we thought, why don't we take the common things that people are doing in streaming jobs, which is basically making sure that you're checkpointing your data the right way so that if the stream fails, you can pick up where you left off, doing some windowing aggregation functions so that if you want to aggregate your data by event time, like every 5 minutes or 10 minutes, you can do that easily. Making sure that you have exactly once semantics, so if your stream fails, you don't have to worry about, did I already process this data or not? So basically, we're building all of that into the API, so you don't have to think about it, it just works. And the idea is that you should be able to take a Spark job that is just purely batch, change a few lines of code, and turn that into what we call a continuously running application. And then finally, with Spark 2.0, we upgraded some of our SQL syntax, so now we're ANSI 2003 ANSI SQL compliant. Really quickly, Couchbase and Apache Spark. So with Couchbase, you're probably using it right now for a number of things. Using it for maybe some user profiles, using it as the backing store for your applications. And then you need to do processing on that data. But it's not efficient to do that processing within Couchbase, because sometimes you need to join that data together for the other data that's outside of Couchbase. That's where Spark comes in. So you can ingest data from your Couchbase database into Spark, join it in with other data from S3, other databases, et cetera, and then build in some analytics. So a couple of examples we have here, recommendations. One of our customers is NBC Universal. They're using Databricks to build a recommendation engine for different shows they think their audience would like to watch. Next-gen data warehousing, Viacom uses Databricks to be able to ingest data from their mobile apps, to be able to do A/B testing to see which shows that they're broadcasting on the mobile apps are getting picked up more often than not. Predictive analytics, Riot Games is another customer that uses Databricks to be able to predict churn in their online games in real time. And then fraud detection. Capital One works with Databricks to be able to detect credit card fraud as and when it's happening. And so just to drive the point home, Couchbase, you're getting data from mobile apps, and you're serving up data back to either laptops or the same mobile apps to be able to use that as a backing store. You want to be able to do analysis on that, but not within the same Couchbase database, and because you want to be able to join in other data, and you can use Apache Spark for that. I think we've already talked about some of this. Is there, for the Couchbase Spark connector, do you want to talk over some of these points really quick?
Sure. So,
get out of the speaker.
Test. All right. So for the Couchbase Spark connector, actually, we started 2 years ago developing the Spark connector. I think it was based on Spark 1.4 or 1.3 when the data frames came out. And we always, when Spark developed a new version, we also built a new one to basically support all the features. So when Spark 2.0 was released, we set out to migrate the code base from Spark 1.6 over to 2.0. And there were quite some changes, right, that Apache Spark made. So one of the big features that we support is now is structured streaming. So as you mentioned before, right, so basically instead of getting a stream of data which is opaque to Spark, with structured streaming, you get this append-only table structure where Spark understands the data, right? So you provided a schema, and then you get this append-only table where you can then do your data frame operations on a continuous stream of changes. Now, where do these changes come from? From DCP, right? So the database change protocol that you've probably seen in the keynote, which is doing all the replication, featuring memory-optimized indexing, right? Feeding all the data out of the key value into your other parts of the system, we are utilizing in Spark to allow you basically to feed the data as it's happening. The mutations are happening on the server. We're feeding them in real time basically into Spark, and then you can do your analytics operations, machine learning, whatever you want to do, basically in Spark with very low latency. And then we also improved DCP handling in general. So previously, the old Spark versions, so if you've used Spark or Spark connector for 1.6, we already had support for regular streaming, but we used a slightly older DCP implementation. So with the new connector, we moved over to a dedicated DCP client, which is, by the way, also used in our new Kafka connector. So if you're using Kafka, the new Kafka connector 3.0, which is currently in a pre-release state, is also using the new client. Also, the analytics service that we're announcing here at Connect is also using this new DCP client. So it's much more mature, stable, production ready, and gives you even better capabilities. And it also supports topology changes like rebalance, right? So that's one of the main features we added for Spark 2.0. Of course, we also made sure that all the APIs are compatible. So upgrading from 1.6 to 2.0 is actually very, very trivial from a user point of view, right?
And then we're going to go into the demo now, but before I do, just kind of like just to kind of show you like the architecture of Databricks for the just-in-time data platform. At your bottom, you've got your storage. So we're going to show you how to connect to Couchbase today, but you might also have some data in other databases, as well as maybe in the cloud with S3 storage. So you can connect to your data wherever resides. Spark is the separation of the compute from the storage. And then you're basically, in Databricks, we orchestrate these Spark clusters in the cloud. So the concept is that if you're a data scientist or you're a data engineer or even a data analyst, you shouldn't have to wait on somebody creating a Spark cluster for you. You should be able to just go through a UI and click a few places and easily create your own Spark cluster, do the work you need to do, and whenever you're done, you just shut it down and terminate it. And on top of Databricks, we have an integrated workspace with notebooks and dashboards. We're going to go through a notebook example today. You can also connect to Databricks via JDBC, ODBC. So if you have your favorite BI tools like Tableau or Qlik, you can still use those as well. And you can build your own custom Spark apps on Databricks as well. Almost everything that I show you on the UI, we also have a programmatic REST API behind the scenes, and you can use that to integrate with a number of things. So now I'm going to take it over to Michael for the demo.
Thank you very much. All right, so what I'm going to show you now is basically how you can use the Couchbase Spark connector together with the Databricks notebook, right? But if you are building your own standalone application, all I'm showing you here, I'm basically running plain Scala code, right? The notebooks are great for visualization, but you can do it in your IDE as well, right? If you're building your standalone Spark application, you can do the same thing there and integrate with all your tools, right? So here we're running a single node on Amazon EC2 just to get some data loaded. So we have our travel sample data, which includes airlines, airports, and so forth. It's the regular data that we're using to basically showcase what we can do. Now, if we go into our dashboard here, the first thing that we need to do is, both in your code when you're doing Scala, is basically do some imports, right? So here I'm importing the Couchbase Spark and the SQL namespace. And the reason is that we provide implicit imports, right? So if you are not a Scala expert, right, or a Scala developer, don't worry. What I'm going to show you is the basic APIs. You can also use Python, or if you want to use the data frames, you can also use basically connect the Couchbase Spark connector with Python, right? So even if you're not a Scala developer, you can use all this functionality from Python and R as well, which is really nice.
One of the nice things about working in a notebook IDE like this is you can basically write a line of code, execute it, get a result, and then iterate it on very quickly, whereas with an IDE, you typically have some sort of compilation stage that you have to go through. And so you can prototype something very quickly in a notebook, and then if you need to, port it over to an IDE and you know, put some more rigor around it. This notebook is in Scala, like Michael mentioned, but you could just as easily create a Python, SQL, or R notebook within Databricks as well.
Yeah. So here we're doing just some imports, making sure that the rest of the demo goes well and we don't have any missing imports. So the Spark connector provides lots of different ways how you can get data out of Couchbase into Spark and how to store data from Spark into Couchbase, right? So at the most basic foundation, you're dealing with RDDs. The big thing about RDDs is that the content is opaque to Spark, right? While they are the most flexible way to do operations against Couchbase, they also put a lot of work on you, right? Because you need to write your map operations, you need to do all the data munging and everything, and you can't use Spark SQL directly. But what it can do is, even if you're dealing with RDDs, you can like do a highly customized nickel query and then take the result out of it and then turn it into a data frame and then hook it into the other parts of Spark, right? So let's start with the lowest level of access and then we gradually go up the stack and do more user-friendly things. So the lowest level and also the fastest way is getting documents by key, right? So we use the Couchbase get method on our Spark context, and we basically tell it here, please fetch me the 2 documents with those 2 IDs. So there are 2 airlines here, and calling collect basically means grabbing the data from all the workers. Now here we're running on a single node, but you can imagine if you run on a 50-node Spark cluster and all the data is distributed and you want to print everything, you need to collect it from all of the workers, right? And this is an expensive operation, so normally you're not doing this because what you normally do is you do aggregations in a distributed system, and then let's say you want to store the results back into Couchbase. Each individual worker would store its subset of the results probably directly into Couchbase, right? But here, if we want to show it, we call collect, and then we print out the results. Now, we only fetch 2 documents from Couchbase, so I think we can handle that in this notebook. So if we run this, what we'll see is actually 2 documents returned, and the JSON document. The JSON document here is a type that is part of the Couchbase Java SDK. And you can see we provide it as a generic argument here. And the Couchbase SDK provides many different types of documents. So there are legacy documents. You can work with binary data, right? This is the simplest case. We basically marshal it into a JSON document, which gives us easy access into the document contents as well, because we'll marshal it for you into a JSON object structure, and then you can grab all the arrays and fields and so forth out of the documents without for you having to do anything in addition. Now, because Couchbase also stores metadata with its documents, so you can see that a document has some other stuff like the CAS value, which you can use for optimistic concurrency, and also mutation tokens. We're not making use of them here, but mutation tokens are a handy way to basically get what we call read your own rights consistency, because as you probably know by now, the indexes, the secondary indexes in Couchbase are eventually consistent, right? So you get a mutation on your key value store, and then we do the replication onto the indexing service, and then once the data is indexed, when you do your query, you get basically what's in the index. Now, if you do a query rapidly right after you key value insert, then it could be that the indexer has not caught up with the records, and then you're probably not reading the data you've written before. Now with this mutation token, what you can do is actually you can say, I'm writing this document, and then I get this token back, and then I'm passing this token to Nickel, and then Nickel will make sure that the index in the background waits until it's caught up to this mutation, and then you can make sure to read the data. So for example, if someone is registering in your application, and then you redirect him to a login page, you want to make sure when he logs in, it actually works, right? And for this use case, you can use a read and writes consistency. That's part of the metadata here. Okay, so that's fine. We can load to documents. That's not too fancy, right? What you can also do, we added this in Couchbase Server 4.5, subdocument. So the subdocument API allows you to manipulate, load, and mutate parts of the document without loading the whole thing. Previously, up to Couchbase Server 4.0, what you had to do is basically load the full document, change the document, and then store it back on the server side. This is one reason why I would use the CAS value for optimistic concurrency, because it could be that in this load, modify, and store cycle, someone else did the same thing with the same document. And to make sure you're not overriding and racing each other, you would use the CAS value to make sure that the document is the same on the server. If it's not, you would basically repeat the cycle, right? And with subdocument, you can reduce that by a lot, because you're pushing this atomic operation to the server side. You can say, please update this field in this document, and then it's an atomic operation on one specific document on the server side without for you having to pull everything down, making the changes, and sending it back up, right? So with this, especially if you're dealing with large documents, you can save a lot of traffic. So if we execute this, what we're doing here is we have 3 arguments to our subdocument lookup. So the first thing is we say, for all the document that is in this list, here we are just touching one document on the server, grab 2 attributes of our JSON document. So grab the name and this other field here, only fetch those fields. And then please also check if this foobar field exists in the document, right? So you can not only load parts from the document, you can also explicitly check if they exist, right? So in the keynote, you saw like the LinkedIn part of the social media. You can check, oh, does this user have LinkedIn set on his profile, without actually having to load the full document. Again, saving on traffic. Now, let's execute this, for example, here in the notebook. So it completed in 30 milliseconds. If we switch over to the UI here, you immediately see we were executing one operation, right, against our cluster. So moving on, Nickel queries. Now, we are still at the RDD level, right? And keep in mind, we'll do data frames in a second. But you can also run raw Nickel queries, so basically arbitrary Nickel queries that you can also execute against the Java SDK and do something with them. So in this case, we are performing a Nickel query which will basically grab airports out of our travel sample data set and then group them by country, right, and order them. So we create our query, and this Nickel query simple here is nothing more than wrapping our query into the structure, because we can also provide arguments to a Nickel query, right? You can do prepared queries, you can do parameterized queries, you can set various options like server-side timeouts and so forth. That's also available in this interface. And then what we do is we actually execute that query. We take the query and then we extract the value out of our query, and then again we collect it and print it out. So this returned 3 rows from our data set. So we have 3 countries, United States, France, and United Kingdom, with a different number of airports. So again, if we check back here, oh, we've seen, okay, there are 2,000 ops per second. And then looking at the Nickel one, we executed one Nickel query. So yeah, the final thing I'm going to show you on the RDD space is you can also execute view queries. So in this case here, we are the same way we are executing a Nickel query, we can call a Couchbase view. So in this case, we say for the design document airports, ask the by location view and get me the top, basically the top 5. Or actually, it's not the top 5, but it's we skip the first 5, and then we want to get the next 5 airports just to make it a little more interesting. So we can query our view, and this returns us the location. So we can see there is airport 1324. It's in France at a city that I can't pronounce. you speak French?
John does.
Okay. So we executed this view query, and if we check back here, so we can see on the travel sample bucket, this is our view that we've created. We published it to production, and then of course we can also, like, this is our view here. So we are meeting the country and the city. So we can do those kinds of very performant aggregation queries right out of Spark. So that's nice, but most of the people these days, they want to work with data frames. And the reason is that data frames are much nicer to use. So in an essence, what is a data frame? It's like an RDD with a schema, right? And this is pretty important because the schema suddenly gives Spark a chance to do something with your data because it now understands what you're actually loading, right? And because it understands the data, it can do all kinds of optimization with like Project Tungsten, doing all the query optimization underneath, right? And even like you call from Python or from R, and then it compiles down to the same underlying execution engine, even if it's coming from Scala, like the Spark SDK and so forth, right? So the first thing we want to do is we need to register our data frames. And so let's look at the first line here. It says airlines equals and then Spark read Couchbase equal to type airline. Now what's going on here? You probably already know that that Couchbase doesn't have a schema. So that doesn't really match up, right? You need a schema with a data frame, but Couchbase is schemaless. So how can we bridge that, right? And what we are doing here is a schema inference. And the way we do it, because most of the time we expect that you have some kind of structure. And what we ask you to do here for automatic schema inference is that you provide us a predicate. Here we are telling Couchbase, I know all my airlines, they have this type field in my documents which equals to airline. And now what we'll do is we'll execute a nickel query to grab the first 1,000 documents which match this predicate. And then all subsequent queries you're performing on your data frame will always include this predicate as well. So basically you can make sure that the predicate that you've defined holds throughout the queries. Now, if automatic schema inference doesn't work for use case because your data is completely diverse, you can also provide a manual schema. So you can do a struct type, and then you can pass it in here, and then it will use the manual schema that you provide. That's also one way to deal with it, but especially for damming purposes, and if your data set is mostly structured, then providing a predicate leads very high accuracy in terms of detecting the schema. So here we are creating two data frames, one for airlines and one for airports. And then what we do is here we register this temporary view so that we can use it in the SQL syntax below. So, okay, so we execute this. Now we can call print schema on our airlines, and we can see this is the schema that got inferred. So if we go back here, so for example, let's look at this airline. So this airline has a name and all kinds of properties, country, call sign, and so forth. And we'll see that in the airline, we also find these properties automatically inferred. Now, what you'll also see is that it supports arrays and nested objects, right? Like we do in Couchbase. So working with nested data works pretty well in Spark. And if you combine it with the nested structure that you can do with JSON in Couchbase, it gives you a very rich way to basically model your data and dynamically query the data. So also, if you look at the query APIs, right, Couchbase and Spark have lots in common, even if one is a database and the other is a data crunching engine, right? Lots of the properties of a distributed system and how we are dealing with data are very similar, right? And this makes a really nice experience if you're developing applications and rapidly prototyping them. What you also see here is a field called meta ID. Now, what is going on here? Now, you know that Couchbase has a unique document ID for each document. And if we would just have all these values basically inside our document and we would not carry the document ID with us, we're probably in trouble down the road if we want to save the document back to the data store because we lost the document ID since it's not part of the document body, right? So what we'll do, or what the Spark connector will do is it will inject this meta ID column automatically and give you access to the document key as well, right? So if you don't need it, you can just ignore it, or you can even remove it from your data frame. But most of the time you want to keep it because then later you have some context if you want to update documents or replace a specific document when you write down to Couchbase. So here is the schema for airports, and we can see that we have a nested structure, right? We have geolocation data as part of our airport, which we can also use like in a spatial query and so forth. So let's do something with it. Now, in the notebook, we can run a SQL query like this. So what you'll see is that we are executing a query. We say select star from airlines, order by name, and then we limit 10. So these are basically we order by name, so we get 10 records from our airlines, and they are properly ordered. Now, if we look at our query UI, sorry, there we are. So we can see we got the query executed, but what you'll see is that we're actually doing two queries. So one is doing the schema inference for this code, and the other one is doing the actual query. Now, if we check the logs, and I hope, let's see.
This is a good example how even though we're in a Scala notebook, we can just do a percentage SQL and automatically start writing SQL. And the same is true if you wanted to write Python in a Scala notebook or R code in a Python notebook. You can mix and match languages within the same notebook.
So let's see. Let's skip that. So, so we are executing the query here basically, and the nice thing is, so you get this table output here, but we can do more fancy things with it than just a query. So here we are doing the same nickel query that we did before on the RDD, but because now Spark understands our query, we can basically do more basically nice outputs. So we do our query, and instead of just displaying our counts with there are 21 airlines in France and 39 in the United Kingdom, we can turn it into pie chart, for example, and we can do other charts here as well.
Yeah, we've got all the basic visualizations you'd expect within like a data exploration tool. But if you want, you can use ggplot, matplotlib, or even D3. Any visualization library that you're using right now, you can just import that and use it inline in the notebooks as well.
Well, one other nice thing we can do is we can do user-defined functions, right? So even if you have some output that, for example, Nickel doesn't provide a function for, right? Or you wanna just enrich your SQL queries in Spark with Scala code. Here we are defining a user-defined function which maps our names, like France, United States, United Kingdom, to their ISO country code equivalents, right? So we map those to like FRA and so forth, and then we register our UDF on basically in Spark. And then now what we can do is we can use this user-defined function here to apply it to our query. And then what we'll get as a result is our UDF, so basically the changed name. And we still get our aggregations and grouping, and now we can do visualizations like showing all the counts and groups by basically put it on the map.
Like
right?
a geographic heat map, essentially.
So that's pretty neat, especially for data exploration, quick prototyping, right? You get very quickly feeling combined with Nickel. And so you get all the power of Nickel, and then you get all these nice visualizations that you can do inside your notebooks, right? So great for data exploration and prototyping. Now, finally, I also included an example with simple machine learning. So there is word2vec. So what we can do here is basically we're doing similarity scoring on reviews. So in our travel sample data set, here we can see a more complex Nickel query that we are directly executing with Couchbase queries. So here we're doing RDDs directly because this kind of query we can't do with Spark SQL because what Spark SQL only pushes down very specific things to their sources. So Spark will push down information to our connector, and this is the predicates and the fields, right? So all the where clauses it can push down to Couchbase and which specific fields we want to do. But for example, it can't push down joins, right? It doesn't push down aggregations. So you either will just take the hit and then Spark will do the aggregations for you, or you craft your own specific Spark SQL, your Nickel query, create an RDD, and then map the results to a data frame, and then basically merge it at the Spark SQL layer. So you get all the flexibility and performance as a trade-off that you can pick, right? Which is pretty cool. So in this case, what we're doing in a nutshell is we are extracting reviews out of our hotels. So every hotel has reviews, And we're using unnest to, and then we are extracting the content out of our reviews. And then we are training our machine learning model here with those reviews, right? So we are storing all this review information in the database, so in our model. Now then we save it, and I think this one is saved to someone on AWS, right? Just as a plain storage mode. And then what we can do is we can load our model, and then we can just call find synonyms for hotel. And if we run this, you get similarity scores, right? And you can see here this one is crunching a little more because it's doing more computation-intensive tasks in the background, and this is all abstracted away from you, right? So for the word hotel, we get our synonyms like property, which has a similarity score of 0.67 and so forth. So now I changed a little bit, and this is a small data set, right? But you can imagine doing the same thing on big data sets and combining the flexibility of Couchbase with machine learning from Spark and so forth. So it very nicely shows how you can take an operation data store like Couchbase, where you can serve millions of operations per second, feed data over structured streaming or using ad hoc queries like Nickel, feed it into Spark, do your machine learning, do your ad hoc queries, even taking data from Hadoop, creating 2 data frames, one from Hadoop, one from Couchbase, joining them together, get an output, and then, for example, storing it back into Couchbase, right? So you can use it as a Swiss Army knife for data integration. You can do all kinds of cool things with Couchbase and Spark together. And we 2 things. So we got great feedback already on our connector. We got good community contributions, which helped us to move to Spark to the dough in a short time frame. And we are actively looking for feedback, right? So the more users we have out there who's trying our stuff, I'm very happy to integrate more features. We are looking especially into integrating full text search into this API as well, so that you get even more flexibility on the data you want to get out of it. We're looking into integrating subdocument mutations as well, so that when you modify your tables, right, and you want to just update specific fields based on those results back into Couchbase, you'll be able to do that. So there's lots of things down the road we want to do, other than, of course, supporting what Spark is adding in new features. For example, structured streaming right now is experimental in 2.0, but I'm pretty sure it will be significantly enhanced in 2.1, 2.2, and so forth. And of course, we'll make sure to align with that, right? So with that, I think we are good on time. Thanks very much. Are there any questions? Yes? Yep.
So I see you're using 2 types of queries, one which are doing aggregation and another one without aggregation. So does this connector have the knowledge of the buckets there and sending the queries which do not have aggregation to the executors, and I can have as many mapper tasks as number of buckets there?
Okay, so the question was, there was one query with aggregation, one without, and I think if I understood it correctly, how it basically maps under the covers to which partitions it sends basically ask the server. So,
so aggregation queries, are they going directly from the driver?
Yes, and where aggregations are going. So when you're using Spark SQL, right, aggregations done in Spark SQL are not pushed down to the Couchbase connector. So what you'll end up is basically you'll potentially pull more data out of Couchbase that you maybe need, right? Or you're not doing the aggregation inside Couchbase if you use Spark SQL directly. But if you use, like, you create an RDD with a specific Nickel query where you do your aggregation up front and then create a data frame out of it, then we basically would do the aggregation on the Nickel side, because then you will already get your aggregated data frame basically coming from the source, right? So 2 different ways. In that sense, the current data frame API from Spark is very generic in what it allows us to basically take or push down. But I'm sure in the next versions they'll extend it to allow us to push even more down automatically, right? So that's the main thing. And then the other thing, I think I really want to mention it because I think it falls into that category, is data locality. So if you're doing key-value operations, both for read and write, what we do is we provide location hints to Spark, because since we're using the Couchbase SDK underneath, we know where the partitions are on the server. Like if you have a 5-node cluster, we know on which node the partition is, and then we know which document maps to the specific partition. So what we can do is if you deploy your Spark workers on the same nodes as Couchbase nodes, what we do is we provide a location hint to Spark saying, you want to probably fetch this document from that specific worker because it's on the same node and then it goes over localhost and you're not having shuffle operations, right? But it's not a hard requirement. If your workers are somewhere else, then Spark will say, yeah, that's nice that you give me this information, but I don't have a worker on that specific node, but then it will fetch it transparently over the network, right? So there are different ways to deploy it, and it depends on the use case which makes more sense. Because if you have lots of network stuff that you want to basically push through, it kind of makes sense to co-locate them. But on the other hand, if you have very computation-intensive tasks and not much that needs to go over the network, it probably makes more sense to do not co-locate them because then they could probably basically interact with each other and taking resources from the nodes, right?
So a couple of things. With anything you can write a nickel query, you can write that, and then the whole query gets pushed down to Couchbase, and it's only the result that gets returned that is materialized in a data frame. Two, like whenever you write Spark SQL, all of the columns that you put in the select statement, those are going to be basically the column pruning that gets pushed down. So you only get those columns returned. And anything you put in the where clause, that predicate push down is going to go to the Couchbase through the Couchbase connector as well. That was the only things I wanted to say about that. I think. Yeah, what was the last question again? About.
I think did we cover everything?
I think we covered it, right?
Second part, where you had discussed selective statement, no aggregation. So the query is getting fired from each of the executables. I get as many members there as a third party in Couchbase that responds that.
Sorry, can you repeat that? I didn't understand.
I have, let's say, simple select query.
Okay.
And I have 5 executables running over there, and for the sake of simplicity, just one core on each of them. So I can parallelly run probably 5 tasks at a time. And those 5 tasks can target 5 partitions in Couchbase for running these parallel select query. So does it work that way, or it's completely different?
So in terms of partitioning, what's going on under the covers is that for nickel and fuse and so forth, we basically have one partition in terms of Spark, like one Spark partition. And key value operations are partitioned into 1024 partitions. That's not coincidence, right? Because Couchbase itself has 1024 partitions. So we map this, for key value, we map the Spark partitions to Couchbase partitions, right? So, but you get the parallelism, right? You can execute more nickel queries in parallel, and then the server will handle them all in parallel, right? So there is not a limitation that you can only run one nickel query at a time or one KV query. So the workers can separately do concurrent things against the database, right?
And one other thing, if you have a particularly heavy operation to get data out of Couchbase, once it's out in a data frame, you can actually cache it in memory, and it'll basically cache all the data in memory across the Spark cluster. And so if you're doing multiple operations against that same data, you don't have to go back to the data source to get the data again. You can just work off the data that's already in memory.
But probably if you have more questions, we should probably follow up offline and figure out the specifics. That's probably perfect.
Did you have one? I think he was next.
Mine was actually very much in that same
Okay.
keeping, which is, avoiding moving data around and whether you can continue to cache it.
Okay.
Okay.
So did the connector work with the data set?
Yes. So yes. So the connector works with the dataset API. It's basically the data frame especially in 2.0 is basically just a data set of type row, right? So the data frames it got changed a little bit in 2.0 because the data set part is now the more generic one, and so most of the code still internally works on data frames, but since it's now just a data set of type row, the bottom line is, yeah, everything works with data frames and data sets out of the box, right? So you can use both on all types of APIs that we provide. Yeah,
in 1.6, we introduced the concept of a data set API, but we couldn't fit it in the way we wanted to because we would break the API, and breaking API changes would necessitate a change in major versions. So in 2.0, we actually made data frames just a data set of type row, and then that's how everything is represented now in 2.0 forward, for if you're talking about data frames.
Yes?
So in the example you showed that automatically you are building the data frame schema, right? But if you are executing a nickel query with an aggregate function, can you apply a custom schema on the data frame?
Okay, so the question was with the automatic schema inference, right? What happens when you do like an aggregation and so forth? So two parts there. The first one is if you do a custom nickel query, you do it on an RDD which doesn't have a schema, right? And then the result, if you turn it into a data frame, you need to provide the schema for that anyways because we don't know how it looks like. If you are creating a data frame through our schema inference, or if you provide a manual schema, so for schema inference, there won't be any aggregations because we are fetching the full documents and grab the columns. If you are doing some more fancy stuff, there is always the option to manually provide the schema, basically, right? So you can always provide the schema manually. If you're doing some super fancy stuff that our automatic schema inference doesn't work with, you can provide that. And it's always, also with structured streaming, the schema you provide doesn't have to be exact. So what happens normally is that also with structured streaming, all the columns that you're not providing in your schema are ignored, and all the documents that are coming back and that are part of your schema, they're just nulled out like in a sparse table, right, that you use in a relational database. And this is also important with structured streaming because with structured streaming, imagine you have this append-only table structure where you have one schema. But with DCP, with our change protocol, there can be mutations coming along from airports, airlines, and so forth, all in one batch, right? So what you have to do there is basically you provide a large schema that covers all the fields you need to. And then down the road, when you do your data frames, and then you can start to select specific parts of your stream, right? You can branch one stream for airports and one for airlines, and then do your custom operations there, right? But the schema is always best effort, right? So if the fields don't exist, they get ignored. And if they do exist, then they're just nulled out if they're not part of the document. Does that answer the question? Perfect. Yes? I think that's one for you, but Spark and R.
So Spark, the question was about R and Spark R in general. So the way Spark works in general is that you have an API for Spark, and you're writing an application, and you're building out this plan of action, right? And the APIs for the particular languages, whether it's Python, R, or Scala, you're using it to build out that plan. But whenever you actually get a Spark action at the bottom where you go to execute that plan, the execution of it takes place within the JVMs across the cluster. So that's why you can write an application in Python or R, and it'll run, the Spark actions will run relatively the same amount of time as if you wrote it in Scala. Now, the only thing is with R, you're probably going to want to take some R functions and turn that into like a UDF. And so if you're doing that, then you're basically going to take that bit of R code, that function, ship it off to every node in the cluster, and then you're going to do some data passing from the JVM to the R to run the function to back to the JVM. So that's one case where, like for UDFs, it's faster to do those in Scala than R. But if you have existing R code, you can still use that in a distributed fashion with Spark. And I think what we found with the customers that are using R with Spark is they basically use Spark for all like the data munging, the data transformations, and so they do that across the cluster and get their data in a format that they want to then run some training on with some R packages they've already been using, and then they can collect that transformed data back to the driver, use whatever R packages they're used to, and then sync the output someplace. So that's kind of how we've seen people using R and Spark so far.
Okay, I think we could take one more. And then
one more.
One more. Okay.
Is that it?
Perfect.
The only thing I'd say is, Databricks, we have a community edition, which is free. If you want to try Databricks out, or you want to try Apache Spark, and you don't want to spin up your own cluster, or have to, do the infrastructure for it, just go to databricks.com/try Databricks and try it out for yourself.
Thank you very much for coming.
Thank you very much. Thank you.